Do we have it now? Yes, there we are. That's a little louder. Sorry about that. So I'll skip back to the start, this start. My name's Zac Hatfield-Dodds. Among my other roles, I don't get paid to work on this, but I'm one of the core developers of Hypothesis. So super excited to be here at PyCon and delighted that so many of you have decided to join me and learn about Hypothesis today. I live and work and grew up in Australia. And in Australia, often we would open by acknowledging the continuing role of Native people in Australia, and that the land that I grew up on just over here was never ceded or taken or in any legal basis handed over. And I think it's important to remember that kind of context. So our goals for today, or at least these are my goals for today, and I hope you share some of them, are to understand where property-based testing might fit into a broader testing strategy for software that you're working on, to understand key concepts in property-based testing and generating test cases, what works and what doesn't. Concretely, I want you to leave with a kind of basic familiarity with the Hypothesis library, what APIs exist, and how to use them. And then the whole point of this is hands-on. You'll actually be ready to test your own projects, whether they're open source, closed source, whatever, using Hypothesis. Sound good? You're all quiet, but some of you nodded. So the running plan for the tutorial is to alternate a series of short talks where I stand up here and tell you stuff, with hands-on exercises where you keep sitting there, I guess, and actually do stuff. So we'll run this in 4 blocks. The first block is just a high-level introduction to property-based testing. I haven't defined this term, but I'm about to, I promise. Then we'll talk about hypothesis strategies, how you describe data, and testing tactics, what kind of properties you test for. And I'll, again, define all of this in a minute. The third block is going to be on the advanced stuff, how you test really complicated programs with a lot of state, or things where you actually have a black box and you don't know what the answer should be. That stuff is still testable, and I want to teach you how to do it. And then the last block is really going to be some open discussion about how to get the most performance out of Hypothesis, how to tell what it's actually doing with your code, how to configure it, and then a little bit about the community. And as I said before, if you have questions at any time, I actually want to be interrupted.
How much of this is going to be covered in the real talk you have coming on Sunday?
The talk I have is basically going to be a cut down version of this. So if you've been in this one, you're of course welcome to come to the talk on Sunday, but if you want to go to something else, you won't miss much that way.
Hi, the slides you're showing, are they part of the repo?
They're not in the repo, but I'll upload them after my talk on Sunday. I just don't want to give everyone spoilers. All right, let's keep going then. So property-based testing 101. You might have seen this kind of graph before. The idea is like you have some problem or task. In this case, you have to write tests. So you go, well, what if I automated this? Instead of like running all my test cases manually every time I change the software, I can use unit test or PyTest and actually have the computer do it for me. But I've still got to spend all this time writing tests. What if I didn't have to write so many tests? Wouldn't that be great?
Yeah.
Awesome. And in the original comic on XKCD, there's like strip 2 where it describes how you spend so much time automating it that you don't have time to do the task anymore. That's my job as the library author. But before property-based testing, I want to talk a little bit about testing more generally, to give you a sense of where this fits. I'm not talking about test-driven or behavior-driven or anything else-driven testing or development. What I'm talking about is the tests you write, not when you write them or how that fits into your workflow. So it should work equally well with whatever kind of development you prefer. Whenever you're testing something, it helps if it's the kind of thing which is easily testable. And there are some systems which are just inherently easier to test than others, but also a bunch of design decisions that you can make and patterns that you can use which make it much easier to test your software. Things like immutable data. If you have a list, it can be mutated, and this can lead to extra bugs if someone else doesn't realize how it's used elsewhere in your code. A tuple will never have that problem. It's got other problems, but not that one. You can use canonical formats where there's only one way to represent any given bit of data. And this means that when you compare stuff, if they compare not equal, you know that they're semantically not equal. If there are multiple ways to represent the same data, if something compares equal, yay, you know it's the same. If it compares unequal, it still might be the same. And so disambiguating that can really help you when it comes to test things. You can do all the kind of standard things that you might have learned in Introduction to Software Development. You can define your interfaces. If you can't decide what your code should do, it's going to be very hard to test that it does in fact do what do you test for? You can separate your input and output logic from the computation that you do. This makes it much easier to test because you don't have to insert mocks for the file system or for network calls. You can actually just pass in the objects that the in and out layer gives your kind of core. Global state makes things hard to test. Randomized behavior makes things really hard to test. But the most important single thing that you can do this evening or tomorrow or when you get home from PyCon is assertions. My favorite definition of an assertion is that it's a statement in a program which is always true unless the program has a bug in it. This is kind of trivial, right? But what it means is that you can insert statements in your functions about properties that you think will always hold. So for example, this number is always positive. My user always has a name. The email address doesn't include spaces. Email addresses can include white space. Did anyone know that? I hope you never have to find out. But where assertions really become valuable is once you start putting data through your program, whether that's in production or with a tool like Hypothesis. When an assertion is violated, it tells you where your understanding of your program doesn't match the behavior of your program. And if that happens at that point, it is way easier to debug than if you read in a log 24 hours later that something went wrong and then a traceback got swallowed and there's a bug, good luck. And so we come to tests, right? If you have assertions in your program, you can also put assertions in your test, which is where we're more familiar with them. And so your test can come from specifying the behavior you want your code to have before you write it, whether that's test-driven development or not. Your test might come from like checking a feature that you just wrote. Or, my personal favorite, you can write tests that defend against possible bugs, especially the possible bugs that just got reported to you. If I'm writing a bug fix, I always try to start by writing a test which fails because of that bug and then fix it. There's a bunch of different phrases to remember what a test kind of should do. And I just want to say, perfectly valid and reasonable tests to write that don't do these kind of pithy things. But they're a good pattern to start with. Some people say given, when, then. Given some input, when I take some action, then I get a particular result or outcome. Or arrange your inputs and your setup, then act, execute the system that you're testing, and then assert that it did what you think it should. Just as a thing of terminology, I'm going to call a test only things which actually execute your code. There are also tools like Pylint or Flake8 or MyPy which will read your code and look for things which are probably bugs or which are hard to understand. I really, really like those, but I'm not going to call them tests for this tutorial. Among other things, you can't wrap hypothesis around them. And a test, ideally, will always fail if a bug is introduced, but never fail if a bug has not been introduced. Can I just see a show of hands? Who here has never written a test which was flaky, that had some kind of random failure that you just rerun it and it was okay? No one? No one at all? Congratulations, I hope it continues. I'm not too optimistic. There's lots of discussion about how big should a test be. From Hypothesis' point of view, these are all the same thing. A test is just something which executes your system, possibly with some extra actions, and then tells you whether or not it did the right thing. Whether the test is a unit test or an integration test or an end-to-end test, it's all the same from Hypothesis' perspective. The only difference will be that one might take a little longer to run and execute more of your code. And then the last bit is kind of what exactly do we check in our tests? And in principle, the answer is literally anything you can observe from code, which when you're testing software is like anything. You could, in principle, test that you get the performance you expect, though those tests aren't always that useful. One really useful pattern is you have some function which takes an input and gives you an output without taking any other actions, and then you can just compare the output to the input, work out whether it's right. Sometimes you have a system which looks something like you give commands to your system and then it's meant to do something. Like you call a download method and it should issue some HTTP requests. And you can test that when called, it does in fact do that. And usually when you're writing a test, this happens by actually turning the behavior you expect into input-output data, because then you can compare it. Easy. But finally, whatever we test should actually be relevant to our users. If we don't care about the property that we're testing, just don't bother writing the test. And so my talk title is Escape from Auto Manual Testing. Has anyone come across this term before? I'm not surprised, because I made it up. An auto manual test, I would think of as a repeatable test. It's something that you could do by hand. You come up with some input. Maybe you think about your code and you work out the edge cases that might happen. And then you actually execute your test function or the bit of code that you're testing. And then you look at the output or the actions it took and check that it seems right. And then you can record this in the form of unit tests or whatever else. We'll call them all unit tests, so that the computer next time can just run the script and do the same tests over and over again. And this is really useful. It means that you can run a suite of like 30,000 tests in a minute or so, instead of taking weeks, which would be awful. But the catch is you still have to have a human come up with the inputs and the outputs and how to check whether it's doing the right thing. And I don't know about you, but when I do this and I forgot an edge case in my code and left a bug in there, I don't usually think of it just to put a test there. So if I forgot something when I wrote the code, I probably had still forgotten it when I wrote the test. So what else could we do? There's a bunch of other kinds of tests which can be really helpful. Diff tests are where you have two versions of something. This might be two entirely separate implementations, or just you've refactored it, and all you want to do is run the same input through both versions and check that you get the same output. This is incredibly valuable for something like parallel code, where you're like, well, if I run it on one thread and I run it on 10 threads, I should get the same output. That one can be hard. Mutation tests actually are a way of testing your test. They go through your code and they'll do things like flip a plus to a minus, or flip a greater than to a less than, and then they run your tests again. And if your tests all pass, this can mean one of two things. The first is that your tests are not powerful enough to catch a bug that could have happened due to a typo. And I'm not going to ask, has anybody here had a typo in code? Because I'm pretty sure what the answer would be. I know I've had them. But the alternative one is that maybe your code is doing something that it doesn't need. So mutation tests can actually give you kind of low-level design feedback about whether your code is more complicated than you need it to be. Doc tests are a kind of auto manual test in that you give it an exact input and output. But where these get really valuable from my perspective is I can put them in the documentation. And then when I run the doc tests, for example, if I get deprecation warnings out, I'm like, wow, I forgot to update the docs for that new feature that I added. And so it's a way of making sure that your documentation stays in sync, as much as it is about testing the behavior of your code. And finally, coverage tests. Has anyone here used coverage before in Python or other languages? Some, but not all. So Python is a tool which will watch your tests being executed and kind of hook into the Python implementation, and it can tell you which lines of code or branches in an if statement were never executed by your tests. Where this becomes really powerful is it actually tells you which lines of code were never executed by your tests. And so by definition, those can't have been adequately tested, right? If you thought you were testing them, but your test didn't even execute them, you've definitely got a problem. Unfortunately, people tend to report this as percent coverage, and for anything less than 100, all you know is like something happened, I guess. But if that number goes down, it could be removed, but covered lines just as much as it could be because you uncovered something important. So if you're using coverage, work out what part of your code is important to test, not necessarily all of it, but then require 100% coverage on that part of your code. Make sense? All right, before we get into the real introduction to property-based testing, do I have any questions about that? No? All right then. So you might remember, auto manual testing, you come up with an input, an action, and an output. In property-based testing, the user does something slightly different. You describe valid inputs. And this could be, my sort function takes any list of numbers or any list of strings. And then you write a test which should pass for any valid input. And for example, maybe this is, when I sort something, I get the same number of each element in the output list. Or my magic fast sort function does the same thing as the Python sorted built in. And then the engine, in Python that would be hypothesis, will generate many test cases for you, randomly according to that description of valid data. Run your test on each input, and then the magic bit is it will report minimal counterexamples. So if your sort function is just like return input, assume it's sorted, it will give you like a 2-element list with the elements out of order. From there, it's relatively easy to debug. This kind of shrinking behavior is not strictly necessary for this style of testing, but it makes debugging it much, much easier when you find a bug. And this is kind of what it looks like in hypothesis. You'll see some of this in the hands-on exercises. We start with imports because it's not built in. Then we have a decorator for our test function, which we call given. So it's given, in this case, any list where the elements are integers and the list has at least one element. Call this function on it. And we could test it in those two ways, right? We could check that the sort function does the same thing as the sorted function, or we could check that we have the same number of each element. And in this case, we could also check that for each pair of elements in the output of our sorting function, the earlier element is less than or equal to the later element. And you don't actually need to be able to write a sort function to be able to check that an output is sorted. This kind of property comes up a lot, and many of the examples I'll describe to you verbally are pretty simple because it's hard to describe the kind of complicated stuff that happens in systems code in a short talk. In the exercises, hopefully we'll get more into that kind of stuff. So, we're up to the first hands-on exercise, the goal of which is really to make sure that you can all install hypothesis, have it installed, have it run, and see it make some tests fail. So if you haven't got this installed yet, or you're having any trouble, just stick a hand up, and myself or Eric will come around and help. Otherwise, let's say 15 minutes for this, and I'll come back up the front when we're ready. Testing. So we're coming up to the time that we'd allocated to the first exercise. Can I just see a show of hands? Who's up to the last exercise here? Or the JSON record? Right. Who's up to the one before that, where you're sorting a list? Yep. Yep. Who here is on the one where you're taking the maximum of the list in the sum? Okay. It's a mix of things. What I'm going to do is, I know that I haven't given you enough time to work through everything, because I wanted to make sure that everybody still had something to work on. So you can take this repo home and keep working on it, or working in a later block as well. But for now, let's go through part of the tutorial. This is more about how you can define strategies for certain kinds of values that you might want, or tactics that you can use to actually write the assertions in your tests. Sound good? The tactics are the bit that people always ask about, but strategies first. As you all know, strategies are how you describe to given. That's basically all they do. They don't do anything on their own, but pass to given hypothesis what kinds of values. This seems to be cutting in and out a bit. All right. One note that I just want to say to you all while I've got a captive audience. I see people construct strategies via private internal APIs. This is bad. Like, the internal APIs change, they break. And beyond that, there's a whole bunch of really complicated stuff about how they work, which is really easy to get wrong, and then your tests mostly only kind of do what you expect them to, so just use the public API. It's a nice API. I like it much more than the internals. You only need the internals to implement the public API, so don't use them, please. The only exception is if you really like type hints, the search strategy type is public enough to use in type hints, but don't subclass it, just put it in type hints, right? Now that I've warned you, you will have seen some strategies for generating values. For example, integers. Along with integers, we've got none, booleans, floats, Unicode strings. We call that the text strategy to give people a hint that your text should be represented in Unicode strings. On Python 3, that's just string. Right, we're coming up to 2020, use Python 3, it's lovely. You can, of course, also generate byte strings or fractions or decimals or date times or time deltas or a whole bunch of other stuff you can find in the documentation. One important note is that even though we tend to have a strategy for each distinct type, a strategy can actually be finer grained than types. You might have seen that the integers takes a minimum value and a maximum value argument. We have that for basically all the numeric or orderable strategies. We'll give you some kind of way to bound the range of them so that you can say things like, I expect this test to pass, but only if it's given positive numbers or numbers less than 100. That can be really useful. And for some types, like date times, it makes sense to pass a time zone argument to that as well as a min value and a max value, but it wouldn't make much sense to give a time zones argument to floating point numbers. So all the values have min and max value, but not all of them have allow nan, that's for floats, or time zones for date times. You also saw some collections. So hands up who generated a list. Good. So the lists strategy takes a strategy for elements. Same thing applies to sets. Dicts takes a strategy for the keys and a strategy for the values, right? It needs both of those. We've got a strategy for iterables, frozen sets, like a bunch of different collection types, but the principle is the same. You give it a strategy for elements, and then you describe the size of the collection. And for the dictionaries, you can also describe the mapping type, because generating a dictionary and then converting it to ordered dict is not the same thing as generating an ordered dict up front. And you can constrain the size. Where this starts to get interesting, which I didn't have you doing in the first introductory exercise, is where you actually want to change the examples that this strategy will generate. And you've got two basic ways to do that. The first is the map method. So you pass a function to map, maybe that's like lambda x, x times 2. So this will actually generate even numbers by generating any number and then doubling it. And hopefully it's clear to you that this will generate always even numbers. Yeah? The other one is that there's the filter method, which takes a predicate, that is a function which takes whatever you generated and returns either true or false, or something truthy or something falsy. And if that function returns false, the strategy will just try again. So you can also generate odd numbers, for example, just by filtering out everything that's exactly divisible by 2. This works, but if you do it with something which is only like divisible by 61, it's going to be really slow, because the strategy would have to generate an average of like 61 things before it found one that it was allowed to return to you. And so hypothesis will actually check for that. If you have a filter, it'll be like, hey, I tried 50 things and I only got 3 back. That's a problem. Yeah?
Is using filter different than using assume inside of your test
Uh,
function?
they're semantically equivalent. So using assume inside your test function is the same as using a filter. But if, for example, you're generating a list of integers with a filter on them, that will be a little more efficient because hypothesis can try elements rather than having to generate a whole list and hoping that they're all correct. But they're implemented the same way under the hood. If you've got like complicated data, which is not just values and collections, we've got a bunch of strategies for that as well. So the simple one is like you have a sequence of things that you want. There's a sampled from strategy, which gives you elements of that sequence. Great for enumerations and so on. Recursive strategies, if you're testing something like JSON data, JSON actually has a recursive definition, right? Hypothesis can just generate recursive stuff. It just works. If you have different strategies, say you want like an integer or a string, you can just put the pipe between them for the OR operation in Python, and you'll get a strategy which can generate either of those things. Or you can pass a sequence of them or multiple of them to the one of strategy, which gives you one of the things you passed it. We try to name our APIs in ways that make sense. If you're thinking about strategies in terms of like sets of values you could generate, though, you can't take the intersection of arbitrary strategies because they could be composed with arbitrary user code and that would just be awful to implement. So we can't do it. What you can do, though, which is super, super, super useful, is the builds strategy. This one, I'll leave you to the docs for details, but you can pass that strategy a callable. For example, a class, and then a strategy for each of the positional arguments that you want to pass that. And keyword arguments to builds become keyword arguments to the things that you're calling. So you can use this to build up instances of any object that you want hypothesis to give you instances of. The final one, which I think is really cool, is often you'll have something in your data which is like a schema, a description in your program of what data is valid or not. You often get this as database tables or as regular expressions or some kind of schema validation library. One thing that's really cool is you can actually write functions which will take a schema and return a hypothesis strategy that generates things which match the schema. From there, if you want things which are like almost but not quite valid, you can just also generate a small edit to make to it. We have built-in strategies for regular expressions. So regular expression, strings which match the regular expression. The implementation is kind of nice for that one because regular languages in a computer science sense have this nice property that it's easy, but Python regular expressions are not regular languages. They're context sensitive and awful. If you use NumPy a lot or pandas, we can generate elements, numeric or otherwise, which match a certain array data type. Or if you are using Python 3 and you like type hints, the builds function can actually work out by inspecting the type hints what arguments it needs to provide. So if arguments have a default value, it'll just leave. Have a required argument, pass a special flag to it, it will actually infer additional things. Yep.
Each time a strategy is run, if I run my unit test multiple times, are the same arguments being generated each time, or are there differences each time it's run?
So by default, it will use a different random seed each time, but in the settings, there's an option to de-randomize it, to seed it off your source code. We tend to recommend randomizing it each time, just as you tend to find more bugs that way for certain very rare things.
Does this interact well with Faker?
Not particularly, because Faker doesn't support the kind of minimization that Hypothesis does. In principle, you could just take kind of the tables that Faker selects examples from and instead select those examples using Hypothesis instead of using random.sample. In practice, we tend to find simpler and easier to understand examples by describing it to Hypothesis directly. Because your code shouldn't depend on something looking like a plausible name, for example. Ideally, you want your code to either handle all ASCII strings or all Unicode strings as names.
Will you take a sort of a philosophy question?
Certainly.
So one of the benefits I find from writing unit test using PyTest or the standard unit test runner in Django is that I'm thinking about the code that I'm testing. I'm actually thinking about what the inputs should be, and I'm looking at maybe the function or the method under test in another window, and I'm looking at the different paths. And for sure, I can miss corner cases, absolutely.
Yep.
But I think more often than not, I actually have, the light bulb go off over my head, and I go, oh yeah, that's right, I missed that thing. And yet here, it seems like it's automated, but I might be thinking less about the code under test. So this is maybe a softball question for you, but could you just compare and contrast those two, and why, what's the argument that this is better than thinking about the code and looking at it as you're writing tests? Thank you.
In the spirit of softball questions, I'll say I actually would say they're complementary rather than this being outright better. And I don't think that Hypothesis could substitute for thinking carefully about what your code should do, right? You need to do both. And even in Hypothesis itself, which unsurprisingly uses Hypothesis to test itself, we have lots of traditional unit tests as well, which cover particular edge cases or base cases or things which have come up in bug reports. So that's indispensable. As to the kind of design side, one of the things I find really valuable at using Hypothesis is it pushes me towards interfaces which are easy to describe. So things where I can say, for example, this function should deal with any string, not just the kind of strings that I've tended to see in production, test against any string, which makes it much easier to think about what's valid and what's not. But overall, there's no substitute for thinking about that and deciding what you want your function to do.
Can I add a point?
Of course.
I've actually discovered bugs using Hypothesis. So things that I hadn't thought carefully about, but should have. Hypothesis gave a tool to discover, oh yeah, there was that corner case that just completely eluded my mind. And so it was a great way to discover the corner cases that I might not have originally been thinking about.
I think I know the answer to the question, but still, for the builds, do we have any restrictions on the types it can generate? So for example, if I want to have custom strategy for data frame generation for a unit test, would that be supported as well?
It is absolutely possible. If you want, we actually ship with a pandas extra. So if you have pandas installed, you can do, from hypothesis.extra.pandas, import data frames. And there you go. You can recursively use builds. So for example, if one of the type annotations is another type, which builds can expect, it will do that and walk all the way down the tree. And you can register custom types as well. So if they're unannotated, you can be like, I know this class doesn't have type hints, but give me that strategy when it's seen in type hints. The implementation of all of that is kind of gnarly and consumed about 2 months of my time a while ago. But now it works beautifully. So speaking of pandas, if you're using stuff that's outside of the standard library, we try not to make Hypothesis depend on that because we want you to be able to use it with minimal dependencies. But if you're using Django or NumPy or pandas or a bunch of other things, especially PyTZ or dateutil, you can automatically get those types out of first-party Hypothesis extensions, which are shipped by default. They just don't get imported by default. If you want other stuff, there's a bunch of other third-party extensions, which we as the Hypothesis authors don't work on, but published. So if you're doing stuff with databases, there's a whole bunch of database layers for models and strategies for that. There's stuff for various schemas, JSON schema, Lollipop, Marshmallow, Protobuf schemas, and so on. And GeoJSON, which is a lovely geospatial format which can contain many more things than most people realize. So, if you're defining your own custom strategies and you have kind of complicated relationships between the data, it's not just as simple as I have this list and each element is completely separate. Maybe you want to generate a string and a valid index into the string. Or you want to generate two numbers where one is always larger than the other, or one is always within a certain range of the other. Generating that upfront and filtering can be very inefficient. So there's two really useful ways to do this. One is the composite decorator. And you put composite on an arbitrary function, and composite supplies a first argument called draw. And you can give the function whatever other arguments you like. And all draw does is it gets you an example out of some strategy. But that means you can construct a strategy which depends on the results from earlier draws. So you can have arbitrary dependencies between your data, as long as they're not like recursively interlaced. But you can do recursive stuff just by having the composite strategy call its own function and then draw an example from it. And that will in fact work. If your data generation needs to be interleaved with the operation of your test, that works too. There's a special strategy called data, which gives you an object which can draw stuff out of strategies. Use this one with caution. It's easy to get into situations where it's just harder to reproduce or to read what data was generated because hypothesis has to log somewhat more information. Sometimes I use it anyway, just because it's faster to toss this off than to write a custom composite strategy. And as long as I don't actually have to debug it, it's fine, right? One theme here I want to say is that that is actually fine. If you're writing tests and they pass, any time that you've spent on optimizing for what happens when they fail is going to be wasted. So maybe just leave yourself some comments about, like, if this fails, here's what I'm going to do to make it easy to understand the failure, then I can rerun the test and debug that instead. So don't do more work than you need to up front. And of course, sometimes you just do need the complex, high-powered data strategy. I mentioned before minimal examples, and you probably saw when you wrote the tests and they failed, they tended to give you like really short lists, where it was hopefully reasonably easy to work out what you'd not thought of. What you need to know about shrinking and strategies is that strategies shrink from the bottom up. So if you have integers and then you map something, hypothesis actually sees that from the inside of the integers strategy. So it will shrink that towards 0, towards positive numbers and towards smaller numbers, without regard to whatever you're mapping over it. So ideally, if you want minimal examples, as I do, make sure that when the underlying strategy is minimized, whatever you've constructed out of it also shrinks in some way. And exactly what shrinking will mean for your customized strategies will depend on how you define them. That's fine, right? It's your test. You should have some idea of what it would mean to have a simpler example or a simpler input, and then just make sure that you arrange the strategy so that that happens. Again though, don't spend too much time on this before you ever see a failure. Among other things, you might not know whether it's actually going to be minimal until then. The final thing there is that because hypothesis runs your test multiple times, it's possible for it to find multiple different exceptions. If so, it will just report each of them to you wrapped up in a multi-error. That basically just works. If you happen to see a traceback that has multiple exceptions printed, that's what's happening. And you can fix those separately or together, and hypothesis again will keep trying whatever has failed before until it no longer fails. The inline data, it's great. Here, for example, you have x and y. X is always guaranteed to be at most equal to y because y is generated with a minimum value of x. So you can express pretty much anything in this system, but if you can, maybe use composite. It's basically the same interface. Any questions about strategies before we move on to tactics?
Can we run with different conditional strategies?
So what do you mean by that?
Different tests to run different strategies for the same test. So
Yeah, so one option would just be to use the one-of, right? So you have one of these strategies for each argument, maybe it ends up being easier to copy paste the text on each. Or one pattern that I've used occasionally is actually to put data on PyTest parameterize over various strategies, which I then draw from inside the test. It's not a really pretty pattern, but it's very concise. Power. All right, tactics then. This is the bit that people always ask about. Like, you have this library, what do I do with it? So I've spoken about auto manual testing, where you check that the output is exactly what you expected. This is great, but obviously hard to deal with hypothesis. There are tests. Does your oracle function, you go into the cave and you're like, is this list sorted? Sometimes. You can have partial specification, where it doesn't tell you everything about whether or not a test is correct, but it can detect at least some bugs. And then later in this talk, I'll cover metamorphic testing and hyperproperties. Super exciting words invented by academics who wanted super exciting names for tests. So an oracle function is amazing if you can get one. An oracle is something which can tell you for any input whether or not your test, like your system that you're testing, did the right thing. Like, this is great. If you have one, you can just test any input, and whether you get the same output or the same error, you're still testing something valuable there. This is really, in real life, this arises when you're re-implementing something that someone else has. When you're implementing performance optimizations, you can keep the simple and unoptimized version. Check that, for example, my fancy thing does the same thing on one thread as on 10 threads. Anyone had threads before? Yeah, the rest of you haven't used threads, have you? One pattern that can be useful, though, where you don't have like a true oracle, is what we call a reverse oracle, which is where you work out the answer that you want and then construct a question. And these examples that I'm talking through are, again, artificial. In your code, you'll recognize these properties in more complex situations, but one case might be if you have something which factorizes. Factorizing a number is actually really hard for large numbers. That's kind of how a lot of cryptography works. But one way you could test this is actually to generate a list of factors, multiply them together, and then test that your factorizing function gets those original factors back. So start with an answer and then look for the question. The downside of this is that sometimes when you have an oracle, you need to test the oracle as well. And you're like, I need tests for my tests to test the thing I'm testing. Sometimes you do. Sometimes the power is indispensable and worth it. Other times, you may just look at this and go, it's not worth the trouble. Testing is kind of specific to the system that you're testing and specific to the level of assurance that you want on it, right? There's not a correct answer, there are useful tools. That's my talk in one sentence. Partial specification can be super useful where you don't actually care about the exact answer, you just care about detecting things which are obviously wrong in some way. For example, if you take the mean of a list of numbers, it should always be at the minimum of that list. This makes sense, right? If your mean is less than the minimum or greater than the maximum, you have some issues, even if you don't know what the correct mean is. And there are a lot of those serialization, so where you dump something to JSON, then read it back in and check that they're the same thing. Those are technically partial as well. In fact, almost all specifications are partial. Even when you have an oracle, there will be behavioral differences between them, something like performance or edge cases or what kind of error message you get. The question is really whether you care about the things which are not covered. And often the answer will be no. But where it is, partial specification can be incredibly powerful. The last pattern that's useful here is what I call a special case oracle. This might be a function that you can only compare your thing to for certain inputs. So for example, if you don't know how to take the maximum, or the largest product of any two elements in the list, if you know they're all positive, you can just sort the list and multiply the top two. If they're negative, then you might have to do that at either end, and you don't know how to do that, and it's kind of complicated. But special case oracles, which completely cover part of your input space, can nonetheless flush out all of the bugs that are in that part of the space. So actually really useful. Sometimes this comes from like where you have a function with multiple parameters to it. If you only vary one at a time, often your test will be much easier to write, or you can write much stronger assertions over the behavior, even if you won't necessarily catch all the bugs. And then the last part of this is kind of properties which come up frequently. So not all code will have these, but lots of code does or could have. Often I find it's actually worth redesigning how I've done some bit of code so that I get these nice properties which make it really easy to test. Does not crash. The simple property that when I call my function with any input that ought to be valid, it does something that is not raising an exception. This one is embarrassingly effective. In fact, this demo on the slide right here crashes. Because it turns out that lists of integers includes the empty list, and if you take the max of an empty list, you get a value error. This is not something that you would always think about when you're talking about the max, let alone with more complex functions. So this is always the first test I write. I don't write any assertions, I just work out what kind of data can I generate, and then I'll call my function and see what happens. Often it's nothing happens, but sometimes it's, wow, that was embarrassing. Sometimes we have invariants in our code, so things which are always true for any input. For example, that the counter, that is the number of each element in any collection, is the same regardless of how you shuffle or sort that collection each time you call it. This seems kind of trivial, right? As soon as you write like a web API, which delivers results over multiple pages, you could have a property like, for any search term, I get the same set of results no matter what pages I ask for, whether it's pages of 7 at a time or 20 at a time, I should get the same things, right? And sometimes you have operations which, if you repeat them, don't do anything else. Like if you take the set of a set, it's round trips are some of the ones which are especially useful because we often end up writing code that has to go to some data store, a database or a network call or whatever else. And all we want to do is transform our data into some other format and then get it back at the other end, whether that's later in time or in a different machine. And it turns out that just generating valid stuff and putting it around these loops can turn up all kinds of problems, as you'll see in the next set of exercises. And this one doesn't have to be like a strict serialized, deserialized call. Sometimes this is like you set a property and then you get that attribute. Or you append a thing and then look for it in the list and it should be at the same index. The final one, and I'll speak more about block of talks, techniques for when you don't actually know what result your code should give you. Where you have a black box function or some simulation, there are still ways to test it. But more on that later. So for the second set of exercises, I'll give us, say, half an hour this time. We'll, in fact, go through to what, 2:55 or so, and then break for some snacks. We'll be in this second file, PyTest strategies and tactics.py. Same process as before. Run it, open it, edit, rerun, you get the idea. Sound good? You're typing, I'll count that. Front. So we're just testing the audio to make sure it doesn't keep cutting out. And this does seem to be good so far. Hopefully the signal's strong. I'm getting some nods. All right. So hopefully we've all got ourselves something to drink, snack on. And I know I at least am ready to get on to the third set of exercises, right? We've got about half an hour left. So let's talk about how to test things that people might call untestable. Like the first question is, are these things actually untestable? And the answer I would say is no, they're just really annoying to test using traditional techniques. Something like a black box function, where for any given input you have no idea what the output should be, and you have no reference, you just know that it does something. Those happen a lot when you're simulating something complicated, in economics or in physics or in fluid dynamics, or if you have a neural network. No one really knows what a neural network is meant to do, it's just meant to give you the right answer by magic.
No, by gradient descent.
Oh, sorry, by tensor gradient descent. Magic. The other thing that's really hard to test is code that manages a lot of state. So stuff with database drivers or devices or network requests, you're like, I know what this should do, but it's really hard to describe it in a test. So let's talk about how we could do these. I mentioned before the phrase metamorphic relations. This was coined by an academic who wanted papers out of his title. Metamorphic relation means a property where you don't know how the input is related to the output, but you know that given two inputs with some relation, you have some idea of what the relation between the outputs will be. So this could be if you take the mean of a list of any numbers, and then you add the mean to that list, you know that you should get the same mean, right? Or if you add a larger number, you know that the mean should increase, even if you don't know what the mean should be after that. That's it. It's really not as complicated as the phrase metamorphic relations makes it sound, but it is super useful in practice. This technique is especially popular for compilers. So for C compilers, for example, people have innocent sounding things, like given any legal program, it shouldn't matter what you compile it with. The machine code should do the same thing. That one tends to turn up a lot of compiler bugs. When you generate random programs using something like hypothesis, and you compile them in various ways, and you just check that they do the same thing. They often don't. You can think of this as a kind of diff testing. So I mentioned before that you could do this with the new version and the old version of one of your programs or functions. Same principle. Another one where I've seen this technique be really effective is in something like a RESTful API. So Spotify, for example, had a bug where the number of results you got from a search would change depending on how many results you asked for per page. And it turned out there was a sweet spot of about like 23 results per page, which would give you more results for your search than any other number. And this is a kind of silly thing to have for a database front end, but it does happen. You can even have properties like adding a search term to constrain your search should lead to at least not more results. You might have the same number or you might have less, but you should never have more. For RESTful APIs as well, don't forget all the standard properties are still helpful. You can have properties about round tripping or about repeating the search and getting the same results, that kind of thing. Neural networks. I can't read this slide. Can anyone else read this slide? The state of the art of testing neural networks and machine learning code is frankly appalling. So if you are doing this, a couple of tips, and God help your soul. Use lots of assertions, like assert everything. Assert things like, when you run a training step, your model should update. It's really easy to forget to connect things or to copy paste a bunch of similar definitions and edit all but one of them. And then you just redefine the same thing twice and it didn't do anything. And the whole thing seems to work, except it doesn't work quite as well as reports indicate that it should. Debugging that is a nightmare. You can simply bound your expected results. You go, I don't know exactly what this should do, but it should be within this range. We've discussed a lot of techniques which can help with that kind of code. So there was this nice property for self-driving cars that someone thought of, which is like, if it uses a video camera to navigate, getting a single drop of water on the lens of the camera could lead it to do various things. Like it might decide to pull over because the weather's bad, whatever, but it shouldn't do like a turn into oncoming traffic. If you feel like going to that link, you can find out that every system they tested did things like that. Stateful testing is where the things you can do depend on the things that you've already done. So calling a function once will not let you solve the Towers of Hanoi problem. What you actually need to do is set up a way of exploring that system through time with state that varies. Because, like the real world, software does in fact have state. Like, things happen over time. Functional programmers like to wrap things in monads or whatever else and pretend that there is no state, but there is. Networks have state, databases have state, the real world has state. Things that update over time have state. This is really annoying, but we have to deal with it and you might as well test it. The trick with generating test cases is to work out how you represent this problem to a tool like Hypothesis or even to an auto manual test. And a really neat formalism for this, and I just want to apologize for computer science jargon. A formalism is a rigorous way of describing the world. It lets us do logic about it, reason about it in various ways. So a non-deterministic finite automata is simply something which has state, and in any given state, there's some kind of choice of actions that it could take. For example, I start with an empty database. It's not valid to look up a key in an empty database, so the only operation I can do is to add a key to the database. Once I have a database with at least one key and one value in it, I can do a bunch of things. I could add another key, I could get the key, I could update the key, or I could delete the key. And so if you represent this using Hypothesis, you end up with a bunch of methods, and it will try adding, updating, getting, and eventually removing. Regular expressions basically work the same way. We can model these things as classes. They have really nice properties to implement, but we don't need to care about it for this. And so in Hypothesis, you can actually represent this using a class, right? A class is a kind of object which has some state, attributes, whether they're global or class or instance attributes, and it has methods, that is, things it can do. And so the trick is pretty simple. You just import the various things from Hypothesis, which you'll see in the exercises again. You set up any initial state. So we say the number starts at 0. And then there are two things we can do. We can take any other integer and add it to the number. This is always valid, right? There's no precondition for adding something to a number. Or we can divide 1 by our number. But that one is only valid if our number is not 0. And so what Hypothesis will do is it will take this definition and it'll go, okay, the number starts at 0. What rules are available? Well, I've got 2 rules, but only one of them is valid. So I'll draw some integer, add it, and then I've got 2 rules. And it will keep exploring, and for this one, I don't think it finds a bug. It seems like arithmetic should keep working, right? I hope so. There are some other ways to do stateful testing. We had a previous thing, which is now deprecated because it didn't work so well. But importantly, the data strategy that I was talking about before for mixing drawing stuff with your test, that's actually equivalent to stateful testing. Because your draws, your data can depend in any way on what's happened so far. If you can, a rule-based state machine is actually more constrained than the data strategy, so it will tend to behave better in certain ways. So for our third exercise, which will take us through till close to 3 o'clock when we're meant to wrap up, we've got a last test file. I'll suggest, depending on what you're interested in, either start with the stateful testing or start with the metamorphic testing. And then if you want to, check out the other one after the tutorial. So we are coming to the end of our time, which means I'm going to tell you the last few things that you might want to know about hypothesis. If you want to hang around for a bit, I'll be around for a few minutes at the end and happy to take any more questions. But let's just talk about like performance things, configuration options, and what the hypothesis community looks like. So the first one is, you might have seen through this that one of the challenges is just working out what your tests are actually doing. If you haven't written exactly what they're going to do, there'll always be that question. And there's a couple of solutions. One is the show statistics option. You see, like, hands up if you saw that or used it. Couple of you, not everyone. It is documented, right? The docs are pretty good. So if you need something, go to the docs, or I've got cards on the table up the back. Feel free to take one and get in touch with me. Performance, like hypothesis is pretty fast, but running your test function 100 times will be slower than running it once. Yeah? There's really not much more to say. If you filter a lot and it has to keep retrying things, obviously retrying things takes longer than doing them once as well. But otherwise, things go pretty fast. When you're shrinking data, when it's trying to find a minimal example, if it's taking too long, it will just bail out and you'll have whatever example it gets to. But the main thing to think about is when you compose strategies, make sure that when the underlying things shrink, the thing that you've mapped over the top or built or put a composite on shrinks as well. If you are using filters, use them sparingly. It's better to do things with map or by construction than by filtering if you can. But when you're using filters, put them as close to the thing you're filtering as possible. So we've got the assume function, which is like a filter that you put in your test case. That works really well. Use it when you need it. But if you can put a filter like on the elements of a list rather than on the list itself, that's a better option. And one pattern, which is sometimes unavoidable, but if you can avoid it, do, is when you draw like an integer size for some collection and then draw that many elements of something. Hypothesis finds it relatively hard to shrink that because you have to simultaneously reduce the number of elements and delete an element. So it's a little more efficient if you can generate a collection of things and the elements of that collection. But above all, like I've said this before, don't spend more time optimizing things than you actually save, especially optimizing things which only matter when your tests fail. Hopefully they don't do that too often. When you need to configure hypothesis, we've got the settings module. That lets you tune things like how many examples it runs. So by default, it's 100. But if I'm just writing something which I'll test once before merging, I might turn that up to like 100,000. It doesn't matter if I take 20 minutes and go get a coffee while my tests run to make me really, really confident that it's doing the right thing. And there's a bunch of other options. So we have like a per test case timeout. So if your tests are really slow, that'll get caught. You can decide where the examples get cached in the database. You can, if you're using a debugger, our multiple bug reporting will often like change the way frames work. So you can just disable that if you're using PDB, for example. When it comes to reproduce failures, you might have noticed that when a test fails and you run the tests again, it fails instantly. That one's because hypothesis actually caches the underlying representation of the test case. And the first thing it does when it runs the test is it goes looking for previous failures in that cache. And if it finds some, it'll just replay them. If it passes, it then goes on to generate more examples. But if that test fails, it just stops immediately. So you get a really fast test edit loop. However, if you're running tests in CI on a remote server, you don't have that cache locally. So there's a couple of things that come in here. The first is that hypothesis will print the little wrapper of the data that failed. So you should be able to just like put that into your test function and see what happened. Maybe you don't even need to reproduce it locally if the logs are good. The second is that we'll actually print the seed that hypothesis used for random generation for that whole run. So you can simply run it locally with the same seed, you should get the same bug, and after that it will be in your local cache. And if all else fails, there's a setting for print blob, which will actually dump like a base64 encoded version of that cache data, and then you can put that in as a decorator, reproduce it, and get on with your day. That one gets kind of ugly, but it's a lot less ugly than having to debug something that only happened on a remote server once. Another tip is, once you're installing Hypothesis, we do recommend staying on the latest version of Hypothesis. It's really well tested. And we release every pull request as a new version. I'll be giving a short talk about that. Saturday, which means that if people report a bug, we typically fix it within a few days, and it's available from PyPI within about 30 minutes of that bug fix being merged. So if you stay on the latest version, you get all the latest bug fixes, along with all the latest features and performance improvements, which is sometimes really nice. Hypothesis will keep working, like I promise. So stay up to date for the sake of your own test suite, the speed, and the features. If it comes to who else uses Hypothesis, like the Hypothesis team uses Hypothesis. Hi. According to the PSF survey this year, about 4% of all people using Python who responded to that survey use Hypothesis too, which is super exciting to me. Many companies use Hypothesis. We've got people on our bug tracker from Uber, Google, Amazon Web Services, and various others who aren't allowed to tell me formally that they use Hypothesis for corporate policy reasons, but I can see their email domain. Something like 2,000 open source projects on GitHub are using Hypothesis, and the Ethereum blockchain uses it too somehow. I feel I should mention, given that I'm giving a talk, that I do offer consulting on Hypothesis as well. So if your organization is adopting it and you want some customized training like this, longer sessions, or just code review of your use, we can do that for you. Both myself and David McKeever in England, who founded the project a few years ago. It's open source. That's good. If you're interested in contributing, new contributors are welcome. Many of our remaining issues are not exactly trivial, but we do also tag the first issues. So if you want to just get started in open source, we can help you with that as well. And Hypothesis, I hope you'll find this helpful, tries really hard to be legible. That is, we try to design the API and the whole library so that things you expect to work either actually do work exactly the way you expect, or they give you a clear warning as to what else is happening instead. So there's a few things which look like they might be reasonable, and if people have reported to us ever, for example, that this seems like it should work but doesn't, or it kind of works but has terrible performance, we either fix it so it works well, or we make it emit a warning so that you know what it's doing instead. That one is rare, I find, but we really care about good error messages, and not just errors, but helping people use it effectively. And the last thing I wanted to talk about today is the bits where I don't use Hypothesis. I've said this a few times. I think it's a wonderful tool, and I really enjoy working with it, but it's not the hammer that makes everything look like a nail. So there are a few things I don't use it for. If I'm simply checking for the sake of test coverage, for example, that invalid inputs are in fact rejected by my function, I don't need to generate 100 or 1,000 invalid inputs. I can just list a couple of things. Use a parameterized test or a traditional unit test for that kind of testing. One that's really useful is where you have a comprehensive test suite designed for some kind of implementation of a standard. Often that means you can just run against 1,000 test cases that are quite widely used. And in that case, I generally use Hypothesis as well, but I'll implement that test first to make sure that I'm testing all of the standard cases that people know can cause bugs. For very slow tests, running them 100 or 1,000 times is just intolerably slow. So I might put that in a little directory that I don't run on every check-in. I just run it. Maybe if someone reports a bug, I'll run that and see if the tests catch it. And for extremely rare edge cases, where the data is complex, sometimes I just can't be bothered describing to Hypothesis what exact kind of data would reproduce that bug. So I'll just do it manually in an auto manual test. So, thanks so much for coming to the tutorial. I hope you've learned something. And I hope that you feel you're ready to use Hypothesis on your own projects. Thank you.